Okay, you got the formula? Can I erase it?
Yeah.
Yes.
Abby, you got it? Almost?
Yeah.
Okay. I want you to give me the word mu, and mu we'll call the first 0 with a sub 1 and the second 0 with a sub 2 so that we can tell them apart. Give me all the arrangements. Abby, I erased this part. It was
No,
8,
you're good. You can erase it now.
8 over 5, which was the same as we had when we did it with the boxes over here. All right, everyone got your mu, M01, O2. Now I want all the arrangements. Here's one arrangement. Abby, give me another arrangement of these 3 letters.
O1, O2.
All right, Allie.
O1, O2.
All right, Bailey.
MO201.
Molly. Gets harder as we go. Oh, she's good.
O1.
All right, I'll let myself figure out the last one. It must be O2, O1M. All right. So there are 3 objects, and we gave all the different arrangements, and we came up with 6. Except in real life, O and O are not distinguishable from one another. So if I erase these, I have some repeats, do I not? So let's cross out, or is there another mu? Yeah, so this was a repeat, so I'm going to cross out this one. Is a repeat, and omo is a repeat. So we only end up with mu, and omo. All right, so this brings up another thing that we have to learn, and this is called distinguishable permutations. You can still keep, if you run out of your page, let me know. These are called distinguishable permutations, and they involve a situation where objects are identical to one another. So like this O and O are identical, so we can't really say that we won't be calculating it like 3, 2, 1, because there are some that are repeated. How will we calculate it? It's easy when you have just this, we could write them out, but even if I added a 4th, it would take a long time to do. So this one we will do by formula, and it is n factorial, which is the number of objects in the problem in the total, whether they're repeated or not. So that would be a 3. N is 3 for our mu problem. Divided by n1 factorial, n2 factorial, n3 factorial, ... And these little n's down here are the numbers that are alike. So in this problem, it would go like this. That's kind of hard to explain, that formula, unless I match it to a problem or two. So our n is 3 in this problem. And our numbers that are repeated, how many m's are there? There's only 1. So 1 factorial, I don't count the ones. But how many o's are there? There are 2. So I end up dividing by that. And there's no other repeats. But this formula is set up for as many repeats as there are. So does that come out to 3? 3 factorial divided by 2 factorial? All right, it does. All right, I'm going to save this formula and erase the problem and give you another one. From mu to banana. Write the word banana. You got to spell it right though.
How do you spell it?
B-A-N-A-N-A-N-A-N. I never know when to stop. B-A-N-A-N-A-N.
We're going to do this, instead of listing them, we're going to do by formula. So, what goes up here? Molly, what did I say the n was?
It's just all of them, right?
It is. So how many letters in this?
1, 2, 3, 4, 5, 6.
6 factorial. So that's the total number of objects, whether they're repeated or not. But when we jump down here, these are the repeated guys.
So is that just, would you just say 2?
Like, so there
Or-
be, I sometimes I do write my ones just to keep from being confused. I go to the first letter, I say, well, there's 1b, so I indicate 1 factorial. It's not going to change anything. Then I go to my a's, how many?
3 factorial.
And then my n's,
2 factorial.
and I think that's all. Right? So,
And then you can cross out the 6.
well, the 6 and the 3 and the 2 don't cross out, but you can take 6 factorial down to 3, 6 times 5 times 4, and stop at 3 factorial. And so then you can cross out the 3's. 2 factorial happens to be 2, so I can factor that into the 4 by a 2. 6 times 5 times 2. What's that, 60?
60.
Alright, let's see if I got that. I did. Alright. So as again, I'm just sort of a shotgun approach. So we've done like 3 topics already, and we've got one more. The last thing I want to teach you today is not a permutation, but it's called a combination. Let me show you. So I'm going to call this. We're going to exit from permutations. Still on this page is still counting if you can fit it. And permutations to combinations. A combination is used when order doesn't matter. And up here, permutations, order did matter. That's what we were counting, different orders. Order matters. So it mattered which horse came in first, second, and third. So, well, what's a situation where order doesn't matter? Suppose out of you 4 of 5, we'll count Hannah. Hannah should be done by now. All right, where are you, Hannah? Suppose out of you 5, I'm going to pick a 3-person committee, and you are going to make up the final for me. So I'm very lazy. So, so let's say I picked Abby, Allie, and Bailey. Is that not the same combination as if I took Bailey, Abby, and Allie? So the order doesn't matter. So the combinations are used when order does not count. So if I was making a committee out of people, I would have to calculate it not like I did permutations, but as I'm going to show you in a second with combinations. So let's do 1. I will say, let's do 1 like that. I think that would be the best. I know, cards. The cards would work that, wouldn't they? Suppose, here's an example. How many 5-card hands are possible from 52 card deck? From 52. I'll just say from 52, not counting jokers or any other odd things. A normal 52 card deck. Because first of all, the problem doesn't come out and tell you, is this a combination or a permutation? It won't. So you have to think. If I got, let's say, an ace of hearts and an ace of spades. I don't know how to draw a spade. Oh, that's clubs. An ace of, I do remember, it's an upside down heart, isn't it?
With a line through it.
Yeah. And the ace of diamonds, nice hand. And a king of hearts.
How did that happen?
All right. Yeah, it was your lucky day. All right, suppose I handed out the cards in a random fashion and you got these 5. Is this the same hand for you if you got the ace of diamonds first, then the ace of hearts, the clubs, the spades, and then the king? Do you see it's the same hand no matter what order you get them in? So therefore, order doesn't matter. So this is a combination. It is calculated differently. If order doesn't matter, do you think there's going to be more or less than the permutations?
More.
Less.
Yeah.
Really?
Yeah, it's sort of like, let's go back to the example with the committee. Like if I was doing a 3-person committee out of you 5, I would have gotten the permutation of 5 things, taking 5 people, taking 3 at a time. I would have had 3 boxes, and I would have had 5, 4, 3. So that. But remember, that is saying that the Abby-Alley-Bailey combination is different than the Abby-Bailey combination. So we don't recount those. They all become one possibility. So there's going to be a lot less combinations. So less, more. All right. So let me show you how to calculate it. Here's how I calculate them. So this would be the combination, it's written with a big C, of 52 cards, taking 5 at a time. And I would actually calculate it as if it is permutations for the first minute. So down here I give myself 5 boxes. And how many ways can I fill in? The first, the second, the third, the fourth, and the 5th. But that's how I would do a permutation. And I just told you there's a lot less. And so what I need to do is divide that number by something to get it correct. And it's always this number factorial. So I calculated just like permutations, but then I lower it because I expect it to be a lot lower. And it's always right if you divide by this number factorial. So I think that's all I need to tell you. I guess I give you the formula for this. Remember the raw formula? And that is n objects taking r at a time. It's going to be n factorial divided by n minus r factorial. Isn't that exactly like permutations? Mm-hmm. And then I put in another r factorial in the bottom to make it lower. So if you prefer to do it with just a formula, you may. I recommend just kind of the understanding that this method provides. All right. Okay, Hannah, since you're in the room, we're going to cut down this video, and you're going to do it. Thank you.